Thank you for coming today. Our second presentation is Deadshot, and our project manager is Garrett Weaver.
Thank you, Dr. Benavides. Good afternoon, everyone. My name is Garrett Weaver, and I'm the project manager for Laniakea Aerospace, and welcome to the preliminary design review of Deadshot. Now, an overview of this presentation, we'll be going over the mission concept, concept of operations, system definition, subsystem definition, the subsystem numerical validation, the system numerical validation, as well as programmatics. Now, at this time, I'd like to introduce my assistant project manager and lead integrator, Mitchell Lydiard, our electronics sub-team lead, Lisa Garside, and our deployment sub-team lead, Vincent Morin. Now, Deadshot will be an impulse launch targeting platform capable of impacting its target with a kinetic impactor at a range of 50 to 100 meters. In our CATIA rendering, we have highlighted some key components: the air compressor, which will fill the auxiliary air tanks, which will provide the impulse to those projectiles, the base, which will be made level by adjustable feet, the electronics box, which will house all electronics, the mount, which will support the launch guide system, and the wind velocity sensor. Now, under our primary objectives, our primary objective is one stated by the Embry-Riddle Aeronautical University Aerospace Engineering track, Astro track, as one that is required for mission success. All projectiles should be deployed using a single impulse. All projectiles should be capable of recording acceleration data during the mission, and all projectiles should achieve an altitude that is less than 100 meters during the mission. Now, all projectiles should be capable of surviving more than 100 deployments, and all projectiles should impact their respective target with an air that is less than 10 meters in length. And then the system should be capable of completing a mission in under 1 minute. Now, the system should be capable of completing a mission in safe wind speeds, which is defined as 16.1 meters per second. And the system should be capable of completing a mission at negative 20 degrees Celsius and positive 40 degrees Celsius. The system should be capable of completing a mission in moderately rainy weather conditions, which is defined as 0.76 centimeters per second. And the system should be capable of delivering projectiles to targets that are greater than 50 meters away and less than or equal to 100 meters away. And the system should be capable of surviving more than 100 deployments. Now, on to our secondary objectives, which are expected for mission success, that all projectiles should impact their respective target with an air that is less than 5 meters in length. Now, onto our tertiary objectives that are desired for mission success. All projectiles should impact their respective target with an air that is less than 1 meter in length, and the system should be capable of completing a mission in full autonomous mode, and the system should be fully validated by April 28, 2017. Now, onto our concept of operations, we have broken it up into 3 different sections: the pre-mission, the mission, which will have a 1-minute time frame, and the post-mission. In the pre-mission, we will collect target location, gather initial wind velocity, pressure auxiliary air tanks, perform trajectory analysis, and orientate the system for the first launch. Now, on the mission, again, which has a 1-minute time frame, which will begin with the deployment of the first projectile, we'll then update the second deployment trajectory, orient the system for the second projectile launch, deploy that second projectile, and repeat those steps for the third projectile. Now, in our post-mission, we'll retrieve our projectiles, locate their initial landing position, extract acceleration data, analyze that acceleration data, and determine projectile velocity and position during its flight. Now, in our design structure tree, we'll start with the base, which will support all other components of the system. Next, the projectile payload, which will record acceleration data during the mission. Now, the data center will be responsible for receiving target location and wind velocity and performing trajectory analysis. It will then send information to the positioning mechanism and impulse supply. The positioning mechanism will orientate the system to the proper azimuth and elevation angle, and the impulse supply will fill those auxiliary air tanks. The projectile will then be launched, and then a proper flight path will be imparted by it by the launch guidance component. With all 3 subsystems fully operational, Deadshot will be able to complete a successful mission. Now, as you can see in our CATIA renderings, the top photo shows its pre-mission stage, where it is gathering that initial information. In the bottom left, you see that it is orientated itself for the first launch, and in the bottom right, it is launching that first projectile. It is then flying through the air, which is small because it is only a 2-inch projectile, and then the projectile will then impact its target. This can be seen in this CATIA rendering of our project, where it orientates itself for the first launch, launches that projectile, then reorientates itself for the second projectile launch, launching that second projectile, and then reorientates itself again for the third and final projectile launch, firing itself, and then returning itself to home. Now at this time, I'd like to introduce Mitchell Lydiard to discuss system definition.
Thank you, Garrett. My name is Mitchell Lydiard. I'm the Assistant Project Manager for Laniakea Aerospace. And I'll be going over the system definition. But first, I'll be introducing the integration team members. First off, we have Annika Howell, David Shavat, and Nicole Schreiber. All right, quickly looking over our CATIA rendering here. The general process of the mission will be we fill up our auxiliary air tanks with this air compressor provided by the Embry-Riddle machine shop. All that air is being managed by the solenoids that are grouped back here. When ready to fire, the platform will be rotated by a turntable and gears on the bottom of the platform. This will aim the system, and then when we're ready to fire in elevation, it'll be raised. These barrels will be raised by the elevation mechanism on the side. And then to fire, the compressed air will be released through the auxiliary air tanks, through those barrels, and fire. Electronics for the system are stored in this box here in the center, and a laptop is in this box on the side. It's going specifically into the electronic subsystem. They have the wind velocity sensor, which is collecting that wind weather data. Their power converters are in the center, and they are connected by wires to all systems that require power. In the center is the electronics package. This does a lot of the thinking of the system, while the laptop or data handling system here, this is doing trajectory analysis. And then finally, the electronics is managing those projectile payloads inside the projectiles. Next, looking at deployment, they're in charge of the air compressor, which once again loads those auxiliary air tanks with compressed air through the solenoid valves at the base here. Sprinkler valves, which have a larger pipe to allow faster air decompression, are connected to the barrels themselves. There's the launch guidance, which fires projectiles through a savo cup. This savo cup keeps them snug in the barrel and on the right trajectory, and the projectiles themselves are fired. And then for the structure subsystem, this consists of the adjustable feet on the bottom. These allow us to alternate the angle of the platform so we can sit more level on uneven ground. The base is a 4x4 foot platform to provide enough space to mount all components. On top of that is a 4-foot turntable, 4-foot in diameter turntable. This supports all components that need to be rotated with the system. And then the mount to hold up the projectiles or the launch guidance subsystem up here. I'll now pass it off to Lisa Garside for the electronic subsystem definition.
Thank you, Mitch. Good afternoon, everyone. I'm Lisa Garside, and I will be discussing the electronic subsystem definition. First, I'd like to introduce my team members. They are Bryce Chanis, Carl Leek, and Ryan Miller. Moving on to the electronic subsystem requirements. Our first 3 requirements satisfy that we operate in all weather conditions as per the customer request. The first requirement is that we be able to complete a mission in a rainfall rate less than 0.76 centimeter per hour. This value stems from the American Meteorological Society's definition for moderately rainy, and we went with moderately rainy because higher rainy weather conditions did not have an upper bound. The next 2 requirements are that the electronic subsystem shall be capable of completing a mission between the temperatures of -20 degrees Celsius and 40 degrees Celsius. These are the highest and lowest recorded temperatures in Prescott. The electronic subsystem shall be capable of measuring wind speed with an error that is 1 meters per second or less, and shall be capable of measuring wind direction with an error that is 10 degrees or less. These values stem from simulation where we compounded our error expected from all of our measurements that still enabled us to meet our system level tertiary objective, which is that all projectiles will land within 1 meter of their respective target. Next, the electronic subsystem shall be capable of measuring wind speeds up to 16.1 meters per second. This value is the highest recorded wind speed in Prescott in the last 5 years for wind. And this is because we only went with the last 5 years since Prescott has experienced land hurricanes in the past, thus greatly skewing the wind speed data. All projectile payloads shall be capable of measuring acceleration data for 10 minutes. 10 minutes was chosen because it is enough time to turn on the projectiles, turn on the rest of the system, walk a safe distance away, and have the mission commence. The electronic subsystem shall generate all finalized trajectories within 30 seconds. 30 seconds was chosen because it fits within our 1-minute mission time frame. Now I will be going over the electronic subsystem visual description. As you can see here, the electronic subsystem has two components. They're the projectile payload and the data center. This is a CATIA rendering showing all of the components within the electronic subsystem. Specifically, the projectile payload, it has 4 elements: microcontroller, a 9-degree of freedom IMU, power, and storage element. You can see in this CATIA rendering how all of those elements are exploded to give a better idea of their size against each other, with the projectile payload hemisphere in the back. First, the microcontroller is responsible for gathering the data from the 9-degree of freedom IMU and transferring it to be stored on a storage element. The 9-degree of freedom IMU has 3-axis in magnetometer, 3-axis in acceleration, and 3-axis gyroscope, and it records the acceleration data from the flight path of the projectile. The power is responsible for giving power to all of the projectile payload elements, and the storage element is responsible for physically storing the data gathered by the 9-degree of freedom IMU. Thus completing the projectile payload, you can see them all assembled within the projectile payload to give a better idea of spacing. Moving on to the data center, here is a CATIA rendering of only the data center elements. First, the azimuth motor controller receives commands from the data center microcontroller and transfer them to the azimuth motor, enabling the launch guided system to be positioned in the azimuth direction. The elevation motor receives data from the data center microcontroller as well and relays it to the elevation motor so it can be raised. The wind velocity measures wind direction with the wind vane and wind speed with the anemometer, and locates it to the data center microcontroller so it can later be used in trajectory analysis. The pressure transducers measure the pressure within each of the 3 auxiliary air tanks independent of each other and relays it to the data center microcontroller as well. The barrel position determination element lies on the front of the barrel positioning, so the launch guidance system, and it locates where the barrel is physically located at that time, both in azimuth and elevation. The data center microcontroller communicates between the data handling element and the various motor controllers, sensors, the AC to DC power converter, and the power control. The data handling is a laptop, and it is responsible for generating all finalized trajectories of the projectiles. The AC to DC power converter takes the incoming AC power and converts it to DC so that the elements within the data center can use it. And the power control are Darlington arrays, and they receive commands from the data center microcontroller when the sprinkler valves and the solenoid valves from the deployment subsystem need to function, and it ups the power so that they have enough power to complete those functions, thus completing the data center component. At this time, I'd like to hand it over to Carly to discuss electronic subsystem numerical validation.
Thank you, Lisa. My name is Carl Leek, and I'll be discussing the electronic subsystem numerical validation. Throughout this section, you will see a requirement listed at the top. Below that, the design metric that we used to validate that numerically validate that requirement, and a table that shows how we numerically validated that requirement. Our first requirement is the electronic subsystem shall be capable of completing a mission in a wind speed of 16.1 meters per second or less. The design metric that we chose for this requirement was maximum operational wind speed. Our wind sensor is able to operate in 89 meters per second. You'll notice that this is a very large factor of safety. However, the wind sensor was also chosen to meet accuracy requirements, which we will see later in this section. Those requirements required us to have a wind sensor capable of being that accurate, which also ended up giving us a large factor of safety on maximum operational wind speed. The next requirement is that the electronic subsystem shall be capable of operating at a temperature that is greater than negative 20 degrees Celsius. For this requirement, we use the design metric of minimum operating temperature. As you can see from the table, all of the elements and components to the left here are able to meet that requirement. The data handling, which is our laptop, can only operate at temperatures greater than 0 degrees Celsius. Therefore, this will have to be insulated in temperatures that are below 0 degrees Celsius. And the remaining elements, which are the SD shield, projectile power, and AC to DC converter, do not have these values listed in the data sheets, and they're also not available through customer service. Therefore, these elements will have to be experimentally validated. If it is found that these elements cannot perform at low enough temperatures, they will also have to be insulated, similar to the data handling element. Next requirement is that the electronic subsystem shall be capable of operating at a temperature that is less than 40 degrees Celsius. This is very similar to the last slide, where many of the elements meet that requirement. The data handling, again, can only operate at 30 degrees Celsius, so in temperatures warmer than that, you will have to put it in an insulated box that contains ice packs and a fan to provide extra cold airflow and keep that laptop cool in warmer temperatures. Again, the SD shield, projectile power, and AC to DC converter did not have these values listed in the data sheets, and they were also not available through customer service. Therefore, these will have to be experimentally validated and insulated if necessary. The next requirement is that the electronic subsystem shall be capable of completing a mission at a rainfall that is less than 0.76 centimeter per hour. The design metric we used for this was the maximum operating rainfall rate. All of our components are electronic, therefore most of them will need to be shielded by some sort of insulating box or insulating material that will keep them protected from the water. The pressure transducer does not have information available on the data sheet as far as rainfall or precipitation is concerned. We are in the process of contacting the manufacturer. However, at this time, we do not have that information available. If it is found that they cannot operate in rainfall, then we will cover these similar to the other electronics. And the wind sensor, which is made to be placed on a larger weather station, is capable of operating at this rainfall rate. All projectile payloads shall be capable of recording acceleration data for 10 minutes. For this one, we have 3 design metrics. The first is the data size versus data storage. This ensures that we can store all the data that is collected in those 10 minutes. The second is the maximum survivable acceleration. All of the electronics on board the projectile payload need to survive the impact. And thirdly, the power consumed versus power supplied. We need to be able to provide enough power to all of our electronic elements for this 10 minutes in order to be able to record acceleration. The first of these design metrics is shown in this table. The IMU produces 0.29 gigabytes of data throughout those 10 minutes, and we are capable of storing 4 gigabytes. Therefore, we are able to store all the data produced in 10 minutes. From this chart, which is the expected projectile impact deceleration, we can see that the maximum expected deceleration is 4,807 Gs. The IMU is capable of handling 10,000 Gs. However, the remaining components do not have this value listed in the data sheets, and they are also not available through customer service. Therefore, these will have to be experimentally validated. The final design metric, which was the power produced versus power consumed, shows that the IMU, microcontroller, and storage elements all use 170 milliamp hours, and we are capable of having 260 milliamp hours from our projectile power. Therefore, we are able to power all those elements for 10 minutes. The next requirement is the electronic subsystem shall measure wind speed with an error that is less than or equal to 1 meter per second. Our wind sensor is capable of attaining this accuracy requirement. The electronic subsystem shall be capable of measuring wind direction with an error that is less than 10 degrees. Our wind sensor is capable of doing this within 7 degrees, therefore we numerically validate this requirement. And finally, the electronic subsystem shall be capable of generating all finalized trajectories in 30 seconds or less. We use the tick and talk feature in MATLAB along with the current simulation that we are using to generate those trajectories, and we're able to do that for all 3 projectiles in 13.34 seconds, thereby numerically validating the requirement. At this time, I'd like to pass it off to Vincent Warren for the deployment subsystem definition.
Thank you, Carl. My name is Vincent Morin, and I'll be discussing the deployment subsystem definition. First off, I'd like to introduce my team members, Lily Giese and Liam Noon. On to the deployment subsystem requirements. So first off, the deployment subsystem shall be capable of launching projectiles to 50 meters, from 50 meters to 100 meters from the platform. It should also be capable of deploying 3 projectiles to their respective targets in a 1-minute time frame. The deployment subsystem shall also be capable of performing a mission in wind speeds less than 16.1 meters per second, as well as operating in temperatures greater than negative 20 degrees Celsius and less than 40 degrees Celsius. It should also be capable of completing a mission in rainfall rate less than 0.76 centimeter per hour. The subsystem shall also be capable of deploying a projectile to impact the target within 1 meter of itself. And finally, the projectile shall be capable of surviving a maximum impact stress of 194 megapascals. So on to the deployment subsystem structural tree. It has 3 components, the first being the impulse supply. The impulse supply component, the purpose is to generate store, and deliver compressed air throughout the deployment subsystem. Looking more into the impulse supply, it's made up of 6 elements, the first being the air compressor. This compresses air to 125 psi in its 27-gallon air tank. The auxiliary air tank is a medical oxygen tank. It is used to store compressed air for each projectile. The solenoid valve is used to open and close the air channels to allow air pressurized from the air compressor to the auxiliary air tank. The solenoid valve also allows air from the auxiliary air tank to bleed out in the event that the pressure inside of the auxiliary air tank is too large. The solenoid housing exists to insulate the solenoid valve from excessive rainfall as well as excessively low temperatures. The sprinkler valve is different from the solenoid valve in that it has a larger orifice. Now, we needed that to increase the flow rate from the auxiliary air tank to the launch guidance component to impart a proper impulse on the projectile. And lastly, the air channels. These provide a pathway between various elements and components within the impulse supply component. And that completes the impulse supply component. The next component in the deployment subsystem is the projectile component. This is a metal sphere, 5 centimeters in diameter. It's a low-carbon steel. The purpose of this is to protect the electronics payload so that it can record and store data throughout the entire mission. And the last component is the launch guidance component. It is composed of 3 low-carbon steel barrels. They're 3 feet long, and they're about 2.5 inches inner diameter. And it only has one element, and that's the sabot cup. Now, the purpose of the sabot cup is so that when the projectile is launched, it doesn't incur any spin from friction between the projectile and the inner wall of the barrel. The reason we don't want spin is because if spin is incurred during exit from the barrel, the Magnus effect will actually change the trajectory of the projectile during flight, thus possibly not meeting our tertiary accuracy objective of hitting the target within 1 meter. Now I'd like to introduce Liam Noon to discuss the numerical validation of the deployment subsystem.
Thank you, Vincent. Good afternoon, everybody. Like you said, I am Liam Noon, and I'll be talking about the deployment subsystem numerical validation. So, same format as before. There'll be the requirement up above with the design metric underneath, and then we'll talk about how we validated that requirement. So to start off with, talk about how the deployment subsystem shall be capable of launching projectiles to a minimum range that is less than or equal to 50 meters. So our design metric for this is minimum pressure. None of our components or elements have a minimum pressure requirement. The minimum pressure required to reach that 50-meter target is only 92 kilopascals, and we'll go over how we meet that in the next slide. This requirement, the deployment subsystem shall be capable of launching the projectiles to a maximum target distance of at least 100 meters. Our design metric for this is maximum pressure. As you'll see here on our elements and our components on the left-hand side, the air compressor and this data is the maximum pressure that is able to give out. All the other components and elements is the maximum pressure that they are able to withstand within their respective systems. So the maximum pressure that the air compressor can give out is 1,034. The factors of safety are listed on the right-hand side. The barrel and the sabot cup, you'll notice, have very, very large factors of safety. The reason for this is because we're not using a huge amount of compressed air, and they are made out of that low-carbon steel, so they are very strong. But all of these elements and components will withstand our maximum needed pressure, which is 331 kilopascals. Here's a graph that just shows what I was just talking about, our range versus pressure, and we, as you can see, we will be within our tolerances up here towards the 331 mark. Our next requirement, the deployment subsystem shall deploy 3 projectiles in less than 1 minute. Our design metric for this is time. We use MATLAB simulation and the tick and talk feature again to look at how long it takes one tank to decompress with that 1/4-inch diameter solenoid valve from the maximum pressure to the minimum pressure that would be needed to go from 100 meters to 50 meters. The time it takes one tank to depressurize is 1.55 seconds, and each tank will be depressurized at the same time. So the time it takes 3 tanks to depressurize will also be 1.55 seconds. The deployment subsystem shall perform 1 mission at wind speeds that are less than 16.1 meters per second. Our design metric for this is maximum operational wind speed. As stated before by Vincent, the wind speeds, any wind speeds less than 16.1 meters per second will not affect the functionality of any of our components or elements. Most of them are made out of that low carbon steel or rubber for the air channels. The only electronic element that we have is a sprinkler valve and the solenoid valves, and those will both be insulated by the solenoid housing element. Next, the deployment subsystem shall be capable of operating at temperatures between -20 and 40 degrees Celsius. The operating temperature, the design measure for this is the operating temperature, both the maximum and the minimum. As you can see here, the only one that is not up to specs is the solenoids. That is why we have the solenoid housing element, which is going to be made out of insulating foam. Therefore, that will be kept warm enough during the low temperatures. The air compressor and the sabot cup do not have any minimum temperature requirements listed, both either on data sheets or with customer service. So just like in the electronic system, we will have to experimentally validate those. The deployment subsystem shall be capable of completing a mission at a rainfall rate that is less than or equal to 0.76 centimeter per hour. That all weather requirement again that we're coming back to. Our design metric for this is maximum operating rainfall rate. All of our components and elements again are the only electronic component that we have is those solenoid valves, which again will have that insulating element. All the other ones will not be affected by this rainfall rate. And finally, the projectile shall be capable of surviving a maximum stress of 193.6 megapascals. Our design metric for this was ultimate tensile stress, and the ultimate tensile strength of that low carbon steel that we will be using is 440 megapascals, which gives us a factor of safety of a little over 2, which does validate this requirement. At this time, I'd like to hand over to Mitchell Lydiard to discuss the structure subsystem.
Thank you, Liam. As stated, I'm Mitchell Lydiard. I'll now reintroduce the structure sub-team members. We have Monica Howell, David Shavat, and Nicole Schreiber. All right, so going through the structure subsystem requirements. First requirement is that the integrated structural components shall survive more than 100 projectile deployments. The structure shall be capable of orienting the launch guidance to an elevation greater than 0 degrees and less than 80 degrees. This came from our simulation where we determined the trajectories we would need for all ranges, and this determined the angle we would need to elevate to. Structure shall be capable of orienting the launch guidance to any azimuth angle. This is just the necessity to aim at any target around us in a circle. The structural components shall be capable of completing a mission at a temperature that is greater than -20 degrees Celsius and less than 40 degrees Celsius. This is from our all-weather requirement. Positioning mechanism shall retain a pointing accuracy of at least 0.1 degree in elevation and azimuth. This came from the simulation as well, and this was compounded with our other errors to determine the max error we could handle and still hit our tertiary objective accuracy. Structure shall be capable of completing a mission in wind speeds of 16.1 meters per second or less. This is part of the all-weather requirement. The structure subsystem shall elevate launch guidance at 4.5 degrees per second, and shall rotate the azimuth at 9 degrees per second. This is so that for any max range of motion over a 20-second time period, so we can do that twice while leaving another 20 seconds in our 1-minute window to aim or any other motion necessary. Looking at the structure design tree, we have two components, the base and the positioning mechanism. Looking at the overall structure, again, down at the bottom we have our positioning feet attached to the base, both sides the adjustable feet, and they are supporting a turntable that allows the azimuth rotation. We're then placed on a mount to support the launch guidance from deployment, and elevation and azimuth are mounted on here for control. So first we're going to look at the base component. We have 3 elements. Those are the platform, the mount, and the legs. The first element is the platform, base MDF. Platform here is 4 feet by 4 feet as stated, and it's 3/4 inch material. On top of that is a bearing, which is where the turntable is mounted on. This has 100 steel ball bearings within it to allow us to freely rotate all the way around. Looking at the mount, we have our vertical mount and electronics boxes to help support and shield all electronic components. This is where the elevation mechanism is mounted, and through a pin we mount the launch guidance. And then looking at the legs, they are screwed in 3-inch inserts into our support platform. This allows us to adjust on uneven terrain. Now looking at the positioning mechanism component, we have three elements: the elevation mechanism and the azimuth mechanism. First, the elevation mechanism. This consists of a stepper motor connected to a worm that is then connected to a worm gear that is connected to the pivot, which controls launch guidance. This has a 30-to-1 gear ratio to give us torque, and the worm and worm gear design is so that the launch guidance cannot rotate the motor back. Now looking at the azimuth mechanism, on the underside of the platform we have a gear train connected to a stepper motor as well. This goes through an ultimate gear ratio of 17-to-1 to provide us with accuracy and torque. And now I'd like to introduce Annika Howell for the structure subsystem numerical validation.
Thank you, Mitch. Hello, everyone. My name is Annika Howell, and I will be discussing the structure subsystem numerical validation. The first requirement I'd like to look at is the integrated structural components shall survive more than 100 projectile deployments. In order to validate this requirement, we'll be looking at individual pieces of our structure and making sure that each individual piece can withstand the missions. So the first piece we looked at is the feet. Each foot can withstand a force of 7,000 newtons. The maximum force that will be put on all 4 feet at any given time is 3,504. Therefore, the feet will not break. Next, we looked at the deformation in the platform and turntable. Under the same force, the platform will deform 96.5 nanometers and the turntable will deform 319.7 nanometers. These deformations will not impede the functionality of our structure. Next, we looked at the pin that connects the mount to the barrels. The max force that will be on this pin at any given time is 2,250 newtons. We looked at 3 different modes of failure for this pin: shear, tear out, and bearing. All gave positive margins of safety, therefore the pin will not break and the hole holding the pin will not deform. Next, the structure shall be capable of orientating the projectile to an elevation angle between 0 and 80 degrees. Our design metric here is range of motion, and torque. There is nothing in the way of our barrels being able to go from 0 to 80 degrees in elevation. The desired torque for elevation is 0.091 newton meters, and our NEMA 14 motors can provide us with 0.125 newton meters. Next, the positioning mechanism shall maintain a pointing accuracy of 0.1 degrees in elevation. In order to obtain this pointing accuracy, we will need a gear ratio of 18-to-1. This leaves us with no margin of safety, so the gear ratio was increased to 30-to-1 due to manufacturing. With this new gear ratio, we have a pointing accuracy of 0.06 degrees. Next, the structure shall be capable of orientating the projectile to any azimuth angle. The desired torque for azimuth is 7.5 newton meters. Our NEMA 17 motors only provide us with 0.46 newton meters. In order to get the desired amount of torque, we would need a gear ratio of 16.3-to-1. This was increased to 17-to-1, which gives us a torque of 7.82 newton meters, which is more than the desired 7.5 newton meters validating this requirement. Next, the positioning mechanism shall maintain a pointing accuracy of 0.1 degrees in azimuth. With the previously found gear ratio, we have a pointing accuracy of 0.053 degrees. Next, the structural components shall be capable of completing a mission in a temperature that is greater than -20 degrees Celsius and up to 40 degrees Celsius. The first thing we will look at is the temperature-induced deformation in steel and wood. Over a 60-degree temperature change, the max that the steel will deform is 22 micrometers and wood 17 micrometers. This difference of 5 micrometers will be taken into account during our machining tolerances and therefore will not impede the functionality of the structure. Next, we looked at our motors. Our motors are specified to run in temperatures between -10 and 50 degrees Celsius. While this meets our upper bound for temperature, it does not meet our lower requirement of -20 degrees Celsius. Therefore, before performing any mission in temperatures colder than -10 degrees Celsius, our motors will need to go through a warm-up procedure prior to the start of the mission. Next, the structure subsystem shall perform at least one mission in wind speeds up to 16.1 meters per second or less. Our base is low enough and wide enough that it will not tip over during these wind speeds. Next, the structure subsystem shall elevate the launch guidance at 4.5 degrees per second, and it shall rotate in azimuth at 9 degrees per second. In order to have our barrels elevate at 4.5 degrees per second, our motors would need to spin at 153 degrees per second. I apologize, the numbers are switched up there. The motors would need to rotate at 153 degrees per second, and our motors are specified to run at approximately 900 degrees per second, which validates our elevation requirement. In order to have our turntable rotate at 9 degrees per second, our motors would need to spin at 153 degrees per second. Once again, the numbers were switched. Our motors are specified to rotate at approximately 210 degrees per second, which validates our azimuth requirement. Next, I'd like to introduce Nicole Schreiber to discuss the system numerical validation.
Thank you, Annika. My name is Nicole Schreiber, and I will be going over the system numerical validation. First, we will be starting with the system level requirements. All projectiles shall be launched in an impulsive manner. All projectiles shall be capable of recording acceleration data for 10 minutes. All projectiles shall survive more than 100 impacts at a stress of at least 194 megapascals. All projectiles shall achieve an altitude that is less than 100 meters during the mission. All projectiles shall impact their respective targets with an error less than 10 meters in length, and the system shall be capable of completing a mission in less than 1 minute. The system shall be capable of performing a mission in wind speeds that are less than or equal to 16.1 meters per second. The system shall be capable of operating within a temperature range between -20 and +40 degrees Celsius. The system shall be capable of completing a mission at a rainfall rate that is less than 0.76 centimeters per hour. The system shall be capable of deploying projectiles to targets that are between 50 and 100 meters from the platform. And finally, the system shall be capable of surviving more than 100 deployments. Next, we'll be going over the system numerical validation. First, all projectiles shall be deployed in an impulsive manner. This has been numerically validated by the fact that we are using one single impulse of compressed air for each projectile. Next, all projectiles shall be capable of recording acceleration data for 10 minutes. This has not been numerically validated by the electronic subsystem due to the fact that we do not have certain information from the manufacturers as to whether or not some of the electronics will survive an impact. Next, all projectiles shall survive more than 100 impacts at a stress of at least 194 megapascals. This has been numerically validated by the deployment subsystem. Next, all projectiles shall achieve an altitude that is less than 100 meters during the mission, which has been numerically validated by our trajectory simulation, which does not allow any flight paths to achieve an altitude greater than 90 meters during the mission. Next, all projectiles shall impact the respective target with an error that is less than 10 meters in length. This has been numerically validated by all three subsystems. The system shall be capable of completing a mission in less than 1 minute, which has been numerically validated by all three subsystems as well. The system shall perform at least one mission in wind speeds less than 16.1 meters per second. This has been numerically validated by all three subsystems. The system shall be capable of completing a mission in a temperature range between -20 and +40 degrees Celsius. This has been numerically validated by the structure subsystem, but it has not been numerically validated by the electronics or the deployment subsystem. This is also due to the fact that we are missing information from some of the manufacturers of the electronics, and we will have to experimentally validate this in the future. Next, the system shall be capable of completing a mission with a rainfall rate less than 0.76 centimeters per hour, which has been numerically validated by all three subsystems. The system shall be capable of deploying projectiles to targets that are greater than 50 meters away and less than 100 meters away, which has been numerically validated by the deployment subsystem. Next, the system shall be capable of surviving more than 100 deployments. This has been numerically validated by the structure subsystem. Next, we will be looking at how our objectives have been satisfied by a corresponding requirement and if that requirement has been numerically validated. So these two requirements and therefore objectives have both been satisfied, except for recording acceleration data during the mission due to the fact that we are missing information from some of the manufacturers of electronics as to whether or not the projectile will survive an impact, or the electronics inside the projectile will survive the impact. Next, these three requirements and objectives have all been numerically validated. Then, for this slide, the top one has been numerically validated. However, the two requirements relating to temperature have not been numerically validated due to a lack of information from the manufacturers, and this will need to be experimentally validated in the future. These three requirements and objectives have been numerically validated, and the final objective and requirement has also been numerically validated. I would now like to pass it off to Garrett Weaver, who will be going over programmatics.
Thank you, Nicole. I'm Gary Weaver, and I'll be going over programmatics. Now, in summary, Deadshot will be an impulse launch targeting platform capable of impacting its target with a kinetic impactor at a range of 50 to 100 meters. In this presentation, we discussed our mission concept of operations, our system and subsystem definition, and our numerical validation of our system and subsystem. Now, in conclusion, all system level requirements have not been numerically validated at this time due to a lack of information from data sheets or customer service. Now, here's a breakout of our team labor hours being broken up into administrative, technical, management, engineering, and development with a total hours of 2005. Excuse me. Now, here's our system budget. We were allotted $1,500 by the College of Engineering. With our current design, we are coming in at $1,390.75, giving us a remaining $109.25. That being broken up, electronics subteam will require $418.48. The structure subteam will require $265.11. And the deployment subsystem will require $224.16. The rest coming from $60 from integration, a $48 cost for the preliminary design mockup. The detailed design mockup has been allotted $50, as well as the critical design mockup being allotted $15, a program administration fee of $15, and a margin of safety of 15% coming out to $225. Now, lessons learned thus far in this presentation, thus far this semester: meet internal deadlines. Communication is key to success. Important to have open discussion amongst the team. Do not be afraid to ask questions in those open discussions. Document delegated work, and team members need to be proactive. Now, here are a list of acknowledgments. We'd like to thank Dr. Julio Benavides and Dr. Patrick McElwain for their guidance thus far this semester, as well as other staff and faculty, as well as the panelists and audience for joining us today. Now, at this time, I'd like to ask my team to come up, and we'll open up for questions.
All right, nicely done, you guys. Looks like an exciting and different project for a term. But well done on your presentation. You guys did a good job explaining how you're going to do this. I think your methodology is good for a start. With that said, as usual, I have questions. We'll just take it from the top. Slide 12, please. Configuration management is good. Okay, slide 10. What are you guys defining as fully autonomous?
So fully autonomous will be that we personally will go out and measure the exact distance and angle that the target is from the front of the system. And then from there, we'll punch in those coordinates into the data center and then turn on the system, and it'll take over from there, orientating itself on its own.
Okay, so you give it an input, you say what the target is, and it does all that. It does all the targeting and firing on its own.
Yes.
Okay. Okay, just want to get clear on that. So slide 20, please. So I'm looking at those sabot cups, sorry. Could they possibly turn in the barrel?
For how as we have it now, they're covered in felt in order to get a snug fit. We haven't thought of that being a possibility, so we'd have to take that into account in the critical phase.
Okay, I only ask because they're kind of short, so I was just wondering, what happens if if it gets turned and launched?
I'll hand you over to Vinny, and he'll be able to discuss the exact dimensions of those saber cups.
Currently, the bow cups are 3 inches long, so the inner diameter of the barrel is only 2.5 inches, so the possibility of that happening is probably very slim.
Okay, I just didn't have a good idea for scale then, because I was looking at them thinking they're only like an inch long or so. Okay, slide 36, please. So what are your projectiles made of, that outer shell?
Our shell is just made out of a low carbon steel that we have found online. They come in 2 halves, and we plan on machine screwing them together.
Okay, so is the instrumentation inside, how's it mounted in there? I wasn't quite clear on that.
Carl will be able to answer that question.
So the current plan for mounting those inside, what is not shown in this CATIA figure is that there will also be lead shot epoxy inside of the projectile payload. This is in order to pull the center of gravity forward of the center of the projectile and give us a little bit of stability, as well as increase our ballistic coefficient. So that will enclose those a little bit more, and then from there we are planning on sticking foam in between there in order to encase those electronics even further and keep them safe during impact.
Okay. A few other options you may want to consider too. You can pot using epoxy, which is, we've done that before. It's messy, but it really protects it. And then you get really good information too because it's a rigid connection. I'm a little worried about foam because you may not have a rigid connection, so you may not get good data from it. Okay, that's all I have on that one.
I actually have one question, because we considered potting as well. Our only worry was that if we made a mistake on the electronics, now they're encased in epoxy. Is that something that you think that a prelim team, having done this very recently yourself, is that something that we could overcome, doing enough testing the first time and getting it right, and then being able to pot it? Or do you think that there could still be some unforeseen variables, such as a wire slipping out as we pot it, that would cause an issue?
So I don't think we potted as part of my prelim team. This is actually on the job. There's a couple ways around it. You can only pot to a certain level, is one way to do it. You can basically make sure that the components you need to get to are accessible from the potting, so you can put like an insert or something that you can remove later or melt off or something like that. You can use an epoxy that you could degrade, like maybe it's soluble in something. That's an option, although I haven't seen that one yet. And the brute force option is you cut it out. I've seen it done. It's a pain, but it can be done.
Thank you, that's really helpful.
Okay, slide 47. For your instrumentation, or sorry, for your, no, it is your instrumentation. Is there a backup? In other words, if you turn off or it gets hard shutdown during operation and then you bring it back up and it decides that its current orientation is 0 degrees, is there some way to recalibrate or some check to make sure that that doesn't happen?
Carl will be able to answer that question as well.
So in terms of the launch guidance orientation, which is our barrel orientation, on the top there is that barrel position determination, which is a magnetometer and an accelerometer. That will be able to give us a heading and then our elevation as well, and that's used in a closed loop control system to figure out where we are.
Okay, just want to make sure you had some redundancy.
Good, thank you.
Slide 50, please. This was good information to show all of it together. I like that slide. Slide 55, I'm kind of nitpicking here now. Maybe not slide 55. Can you go forward one? Okay, I must have the wrong slide number down. Anyways, there's a point where you're talking about max operational time, and it wasn't listed on the slide. That'd just be a good piece of information to have on the slide. Slide 63, please. Now, it may just be late in the day and I'm forgetting, so please bear with me. But where did 16.1 meters per second come from again?
16.1 meters per second was the highest recorded wind speed in Prescott in the last 5 years.
Okay. Slide 75, kind of another nitpicky stylistic thing. when this slide was being presented, some information was listed off, like diameter and length of the tubes. That'd be good information to have on this slide. It's not the only one that's like this. It's just, this is the one that I thought could really use it.
All right.
Slide 81. Oh man, I got all my tanks. No, this is the right one. So how are you going to make sure those 3 tanks decompress simultaneously and evenly?
So you mean as if we're launching all 3 projectiles at once, or?
Oh, they're not coupled, are they?
No,
each
they're
very
not.
individual. Okay,
They
I
each have
misunderstood
their
that. Sorry.
individual solenoid and sprinkler valve.
Okay, okay, never mind. I misunderstood that. Slide 96, please. So are you making the bearing, or is that being made for you guys?
We have talked with Patrick, and he said it was capable to make the valley for the bearings to sit in, as well as the cutout for that valley.
Okay, cool. I want to see that. I was just looking at it thinking, I didn't know they made bearings that big. Okay, cool. And just for my edification, what is MDF? That was thrown around a few times.
Mitch will be able to better answer that for you.
That's medium density fiberboard. It's basically what that table looks like right there.
Okay, okay. I just wasn't quite sure what you meant when you said it. Slide 128, please. How do you want to experimentally validate?
We would go. Oh, I apologize. We would go into the experimental space systems lab and then use the cooling chamber inside there to test at each individual component, and then pull it out and then quickly test it, or have the whole system, since it is just going to be the electronics, sit inside there and see if they're capable of running.
Okay. I just would have gone ahead and said that then.
Okay.
I thought it was kind of weird that you said experimentally validate without talking about the method.
Okay.
It just stood out to me for some reason. Overall, though, that was really good. All I had were kind of nitpicky things and just concerns, but I look forward to seeing this thing work.
All right, thank you very much.
Okay, so let's work. Few questions. The first one is in general about safety. You have 1 valve per tank. It would be probably nice to have at least 2 or 3 for redundant safety in terms of releasing the pressure of the tanks if something goes wrong.
Each tank will have its own personal solenoid valve that will be responsible for bleeding out if there is a emergency situation where we hit the board switch. It will depressurize all tanks.
But I would go with 2 per tank.
2 safety
Yeah,
solenoids.
because if that
Okay.
valve fail, and you don't know what to have.
Okay, we will look into that.
Yeah, just a suggestion. The other question is, for the precision, if you go on slide 107, 109, I think it's very critical as you did all the math. So now you start on 107 with a 1.8 degree for the stepper angle, for the stepper motor. This was taken from the specification of a specific motor, or you're going to try to buy a motor that has this specification? And how you're going to control the stepper motor?
Carl will be able to answer that for you.
So the stepper motor, from the data sheet, it has that specification of 1.8 degrees, and that is for a full step. We are also capable of doing a half step and thus cutting that error in half. And then for the control of those stepper motors, we're planning on using the azimuth and elevation motor controllers. Those have an IC built in, which plugs into the Arduino system clock. That generates the waveform required to run the stepper motors, and all we have to do is tell it full step, half step, quarter step, etc.
Excellent. So are you planning to have some feedback on that, like with an encoder or a potentiometer?
As far as where the barrel is oriented?
Yeah, because with stepper motor, usually, most of the
Right.
time, just keep steps.
Right, and we'll also have that barrel position determination, 9 degree of freedom IMU on the edge of the barrel, and that will be able to give us feedback back as to where, not only how many steps did we think we did, but where the barrel position actually is.
Okay. Yeah, very good. Now, the other question is the coil of the platform. So the platform is just going to sit on the ground obviously, when you shoot the projectile, there is going to be a recoil for the platform going to move backwards. How you're planning to address the issue? But it's typically ballistic.
So for when we were testing the structural stability, we had applied the recoil force into the maximum force that the feet could have, and then in the feet, which are modeled on here because we made it out of cardboard, but there will be a giant rubber foot that it will sit in to prevent any slippage on the ground.
It's based on friction, basically.
Yes, it'll be a friction-based system.
Excellent. And then, yes, for the platform, did you think about using friction bearings instead of ball bearings, like Teflon? These are really high quality bearings that are perhaps easy to machine or install.
I'll hand that over to you to discuss that.
We had not considered Teflon bearings, and we can add that into our considerations. See if they'll be more economical than large ball bearings. Thank you.
Very good job to everyone. Proud of you, Katia.
That's actually the first thing I wanted to compliment on. It's lots of CATIA pictures. I really enjoyed that. And the second thing I really liked was in electronic subsystem numerical validation. The entire section, it was very easy to see. And when you explain, well, spend more time explaining each slide, that really helped. And the other thing is you used lots of graphs and lots of tables that helped. And it looks like you delved into the hardware specs of all the hardware components, and that was really good. It looks like you don't have as many sensors as the previous team, so your data handling won't be as critical. So how many CEs or SEs or EEs do you have?
We have 0.
Okay, so it won't be as challenging as the previous team. So the other thing is the safety for your subsystem testing. Are you testing it outside or in the lab somewhere? All outside.
For when we're testing the system as a whole, we will be testing it outside, and we will be taking safety precautions to prove that we can rotate in any azimuth angle. We will be rotating and dry firing it, and then for how large our safety circle would have to be if there is a worst case scenario and the tanks are pressurized to maximum and launch that projectile, which roughly comes out at 80 miles an hour. We will be confining it with tension wires so they can only launch in a specific 45 degree direction.
Okay, so are you planning on doing any subsystem tests?
Yeah, we will be doing subsystem tests on each component, but are you relating that to like the pressurization of the tanks themselves?
Just all the different subsystems that you will have, is that all outdoor testing?
I don't believe all of it will be outdoor testing because we will have to use the experimental space systems lab, but majority of it will be testing to make sure that it's rain resistant or wind resistant.
Okay, so none of them will really hurt anything?
No, we'll be taking major safety precautions. That's one of our constraints is we're going to have to follow all the guidelines with the embry-riddle safety.
Okay, very good. And last little bit of suggestion that I have is for your requirement validation or verification. The formatting is kind of inconsistent. Some sections are green arrow, and some of them are yes or no. So it'll help if you actually keep them just consistent.
Okay, will do.
Thank you, very good job.
Thank you.
Yeah, I just want to say awesome job. And could you go to slide 15? 15, sorry. I love the animation. Just because I like catting myself. But this is, I mean, this is good for engineers and also good for future managers, just so they can see this kind of visual. I mean, yeah, just really good. So props on your CAD team.
Thank you.
All right, so for your projectiles, Connor already asked, like, how are they going to be launched in there, how they're going to survive the impact. But one thing is that for data retrieval, really going to be, once it's launched, you go out there, remove it, and then, okay, so you retrieve data from there. Okay, so what happens if a component fails? Are you guys going to have extra?
Right now, we don't have allotted an extra projectile payload. That is something we're looking into reducing our overall budget so that we can afford that increase in another projectile payload if something were to go awry.
Okay, because you guys mentioned that some of these components didn't have data available to you, and you needed to experimentally test and see if it works. So you're definitely going to need some spares. I would recommend it.
Yes, definitely, and that's something we're looking into, or in the process of looking into right now.
Okay. So, yeah, the panelists already asked all the questions I wanted to ask. But yeah, I just wanted to say this was a really good presentation. The transition was fluid. I mean, so awesome job, guys.
Perfect, thank you very much.